Tonight, we are going to travel toward the most distant boundary humanity has ever discovered, the edge of the observable universe. From Earth, that edge appears to surround us in every direction, carrying the oldest light we can see. It seems like a destination, something unimaginably distant, but perhaps still reachable if a traveler had enough time. Yet no spacecraft, no matter how fast or how long it traveled, could ever arrive there. As it moved, the boundary would continue to reform around its new position. Galaxies visible today would gradually disappear beyond its reach, while different regions of the cosmos could become visible ahead. The edge of the universe is not a wall waiting somewhere in deep space. It is something stranger, a horizon created by time, light, and the expansion of space itself. In this journey, we will follow that horizon outward, discover why it can never be reached, and consider what may exist beyond everything we are able to see. When people first hear the phrase "the edge of the universe," they often imagine something almost architectural, a great boundary wall somewhere out in space, beyond which there is simply nothing at all. Perhaps a curtain of darkness, or an abrupt stop, the way a road might end at a cliff. It is a natural image to reach for, because almost everything we experience in daily life has an edge of this kind. A field has a fence, an ocean has a shore, a room has walls. It would seem strange for anything to exist without some kind of boundary marking where it stops and something else begins. But the edge of the observable universe is not that kind of edge at all. It is not a physical structure sitting out there in space, waiting to be reached. It is closer to what we might call an observational limit, the point beyond which light simply has not had time to reach us yet. Nothing stops at that boundary. Space does not end there. Galaxies do not thin out and vanish as they approach it. As far as current understanding suggests, the universe almost certainly continues, filled with more galaxies, more stars, more of the same vast structure we can already see, stretching on far beyond what our eyes, or our telescopes, will ever be able to detect. To understand why this boundary exists at all, it helps to picture the observable universe as a sphere, with Earth sitting at its center. This is quite literally true, in one very particular sense, but it is important to understand precisely what that sense is, because it is easy to draw the wrong conclusion from it. If it appears that we are at the center of the universe, does that mean humanity, or our small blue planet, occupies some kind of special privileged position in the cosmos? The answer, gently and firmly, is no. We are at the center of our own observable universe, not at the center of the universe as a whole. This distinction, though subtle, changes everything. Imagine standing in a very large, very dark forest at night, holding a lantern. The light from your lantern reaches out in every direction, illuminating a certain radius of trees around you. And beyond that radius, everything fades into darkness. Not because the forest ends there, but because your light simply does not reach any farther. If a friend were standing 100 paces away, holding their own lantern, they would see their own circle of illuminated trees, overlapping with yours in places, but centered on themselves, not on you. Neither of you occupies a special position in the forest. Each of you simply sees the portion of it that your own light can reach. This is very close to how the observable universe works, except that instead of a lantern's light reaching outward, it is the light from distant galaxies reaching inward toward us across billions of years. Every point in the universe, every star, every planet, every observer, real or imagined, sits at the center of its own observable sphere. This is not a coincidence, and it is not evidence of anything unusual about our location. It is simply a mathematical consequence of the fact that light travels at a fixed, finite speed, and that we can only ever see as far as that light has managed to travel since the universe began. It is worth sitting with this idea for a moment, because it resolves a puzzle that might otherwise feel unsettling. If every direction we look reveals roughly the same distance to the horizon, doesn't that suggest we are in the middle of everything? It does not. It suggests only that we are somewhere, and that somewhere, by the nature of light and time, always looks like the middle from the inside. A ship far out at sea, with no land in sight, would see the horizon as a perfect circle around itself in every direction. This does not mean the ship is at the center of the ocean. It means only that the curve of the Earth, combined with the height of the ship's deck, produces the same visible distance in every direction, regardless of where on that ocean the ship happens to be floating. So when we speak of the edge we see, what we are really describing is not a physical structure, but a limit built into the very act of seeing. It is a boundary created by combining two very simple ingredients: the finite age of the universe and the finite speed of light. Because light cannot travel infinitely fast, and because the universe has only existed for a certain span of time, there is a maximum distance from which light could possibly have reached us by now. Beyond that distance, there may be more galaxies, more stars, more of everything we already know and love in the night sky. But their light, if it exists at all, simply has not had time to arrive. This idea will return again and again as we continue, taking on new depth and new detail each time. But for now, it is enough to hold this single, quiet realization close. The edge we see is not the edge of everything. It is the edge of what we, from this particular point in space and time, have been able to see so far. Somewhere else in the universe, another observer, on a planet orbiting a star in a galaxy we may never detect, is at this very moment looking out at their own horizon, seeing their own edge, feeling, quite reasonably, as though they too are standing at the center of it all. And in a strange, gentle sense, they are right. So are we. Every observer's universe curves outward from where they happen to be standing, and every one of those universes is, in its own way, equally true. There is a simple fact about light that, once properly understood, changes the way you look at the night sky forever. Light does not arrive instantly. It travels, and traveling takes time. This seems an obvious statement when said outright, and yet in daily life we rarely notice its consequences, because the distances involved on Earth are so small that light seems to cross them in no time at all. Switch on a lamp in a room, and to your eyes, the room appears to brighten instantaneously. In truth, the light takes a tiny fraction of a second to cross the space between the bulb and your eye, so brief a delay that it is utterly unnoticeable and for all practical purposes, irrelevant. But once we begin looking upward rather than around us, this small delay stops being irrelevant and starts becoming one of the most important facts in all of astronomy. Consider the moon. When you look at the moon on a clear night, you are not seeing it as it is at that very instant. You are seeing it as it was slightly more than 1 second ago, because that is how long it takes light to travel the roughly 250,000 miles between the moon and the Earth. It is a small delay, barely noticeable, and yet it is the beginning of a pattern that only grows stranger the farther out we look. The sun is next. Sunlight leaving the surface of the sun takes a little over 8 minutes to reach us here on Earth. This means that whenever you have watched a sunrise or felt warmth on your skin from sunlight, you were experiencing light that left the sun roughly 8 minutes earlier. If, by some impossible event, the sun were to vanish this very instant, we would continue to see it shining and continue to feel its warmth for a further 8 minutes, entirely unaware that anything had happened. This is not science fiction. It is simply what it means for light to have a fixed travel time across a fixed distance. As we move outward from our own solar system, these delays stretch from minutes into years. The nearest stars beyond the sun lie so far away that their light takes several years to reach us. When you look at these stars, you are seeing them not as they are tonight, but as they were several years in the past. Most of the time, this makes very little practical difference. Stars change slowly, over millions or billions of years, so a delay of a few years reveals almost nothing unusual. But the principle remains, quietly, patiently true. What you are seeing is history, not the present moment. Now let us reach further still, out beyond our own galaxy entirely. The Andromeda Galaxy, our nearest large galactic neighbor, lies so far away that its light takes roughly 2.5 million years to reach us. When you look toward Andromeda on a clear, dark night, and under the right conditions, it is faintly visible to the naked eye. You are looking at light that began its journey before modern humans existed. The Andromeda Galaxy you see is not the Andromeda Galaxy of today. It is a photograph of sorts, taken 2.5 million years ago, only now arriving at your eye. And beyond Andromeda, the distances only continue to grow. Telescopes capable of detecting extremely faint and distant light have found galaxies so far away that their light has been traveling toward us for many billions of years, in some cases for nearly the entire age of the universe itself. When astronomers study these most distant galaxies, they are not studying the universe as it exists today. They are studying the universe as it existed in its extreme youth, billions of years before the Earth, the Sun, or our solar system had even formed. This is why telescopes are sometimes described as time machines, and it is a description that holds up remarkably well under close inspection. A telescope does not simply magnify distant objects. It gathers extremely faint, extremely old light. Light that has been traveling silently across the universe for a length of time we can barely comprehend, and allows us to finally receive it, to finally decode the information it carries. In this sense, an astronomer studying a distant galaxy is doing something remarkably similar to a historian reading an ancient letter. The information is real, and it is genuinely informative, but it describes a moment long past, not the present. It may help to imagine this in more familiar terms. Picture receiving a letter that has taken many years to arrive, perhaps sent by a relative from a great distance, delayed by circumstance, only now reaching your hands. The letter is completely genuine. Every word in it was true at the moment it was written, and yet you cannot use it to learn what that relative is doing today, only what they were doing on the day the letter was sent. Starlight works in much the same way. It is an honest message, faithfully carried across space, but it always describes a moment that has already passed, sometimes by seconds, sometimes by centuries, and sometimes by billions of years. There is another useful way to picture this, borrowed from the idea of an echo. If you were to call out across a wide canyon, the sound of your voice would take a certain amount of time to reach the far wall, bounce, and return to your ears. In the moment you hear the echo, you are not hearing your voice as it sounds right now. You are hearing a slightly delayed copy of a sound you made a few seconds earlier. Light behaves in a broadly similar way when it travels across the vast distances of space, except that instead of a few seconds, the delay can stretch across years, millennia, or aeons. Once this idea settles in, it becomes almost impossible to look at the night sky in quite the same way again. Every point of light overhead is not simply a distant object. It is a message from the past, carried patiently across space, arriving at your eye after a journey whose length depends entirely on how far away its source happens to be. Some of those messages are only seconds old. Others are millions or billions of years old. And crucially, as we shall see very soon, this simple fact, that looking outward always means looking backward in time, is the very thing that allows the observable universe to be so much larger than you might otherwise expect. Now that we understand that every glimpse of distant space is really a glimpse into the past, we can begin to ask a more precise question. Exactly how large is the region of space we are able to see? At first, it might seem as though the answer should be simple. The universe, according to current understanding, is somewhere in the region of 13.8 billion years old. Light travels at a fixed, finite speed. So surely, one might reason, the farthest we could possibly see is 13.8 billion light-years in any direction, since that is as far as light could have traveled during the entire history of the universe. This is a very reasonable thought, and it is also, in a subtle and fascinating way, incorrect. The true radius of the observable universe is considerably larger than that. Current estimates place it at somewhere in the region of 46 billion light-years in every direction, giving the observable universe a diameter of roughly 92 billion light-years. This may sound like a contradiction. How can we see farther than light could possibly have traveled during the entire age of the universe? The resolution to this puzzle lies in something we have not yet discussed in detail, but which we will return to many times throughout this journey. The universe has been expanding the entire time that light has been traveling through it. Picture, for a moment, a beam of light setting out from a very distant galaxy not long after the universe began. At the moment it departs, that galaxy sits at a certain distance from the patch of space that would, billions of years later, become our own Milky Way. The light begins its long journey, crossing the space between the two regions. But here is the crucial detail. The space itself, the very fabric the light is traveling through, is not standing still. It is stretching slowly and steadily the entire time the light is in transit. This means that by the time the light finally arrives here, billions of years later, the galaxy that originally sent it is no longer at the distance it was when the journey began. Because space itself has continued to expand throughout the entire journey, that galaxy is now very much farther away than it was when its light first set off. This distinction between how far away something was when its light began traveling and how far away it actually is by the time we receive that light is one of the most important ideas in all of cosmology, and it deserves to be stated clearly and calmly because it resolves what would otherwise be a very confusing puzzle. Astronomers refer to these as two different kinds of distance. There is the light travel distance, which tells us how long the light has been journeying toward us, and there is the present day or comoving distance, which tells us how far away that source actually is right now, accounting for all the expansion that has taken place since the light departed. When we observe the very oldest, most distant light in the universe, light that has been traveling for nearly the full span of cosmic history, the sources of that light are not still sitting at the distance implied by its travel time. Because the universe has been quietly expanding for the entire duration of that journey, those ancient sources have, in the time since, drifted much farther away than the distance the light itself traveled. This is precisely why the observable universe, measured in terms of present-day distance, turns out to be so much larger than 13.8 billion light-years. The light took 13.8 billion years, more or less, to reach us, but the place it came from has, in that time, been carried much farther away by the ongoing expansion of space itself. It can help to imagine an unusually patient letter carrier, walking at a slow and constant pace along a road that is itself slowly stretching longer beneath their feet as they walk. The carrier sets off from a certain point, and after a very long time, finally arrives at their destination. But the road they were walking has grown longer throughout the entire journey. The place they started from, if you could measure it now, is actually much farther from the destination than it was on the day they departed. Because the whole road has been stretching the entire time, not just the portion the carrier had already crossed. This analogy, like all analogies we will use, is imperfect in its details, but it captures something true about the essential shape of the idea. Distance is not a fixed, static thing in an expanding universe. It changes over time, even for objects that are not physically moving through space in any conventional sense. It is worth pausing here to offer some reassurance, because numbers of this scale, tens of billions of light years, can feel overwhelming, even faintly alarming, when encountered for the first time. There is no need to memorize the precise figures, or to feel any pressure to hold them firmly in mind. What matters is the underlying shape of the idea. The observable universe is bounded not simply by the age of the universe, but by the combination of that age and the ongoing stretching of space throughout cosmic history. This combination produces a boundary considerably larger than a simple calculation of age multiplied by the speed of light would suggest. It is also worth noting, gently, that this boundary, the outer edge of the observable universe, does not represent any kind of physical structure. It is not a wall, a shell, or a barrier of any kind. It is simply the outer limit of what light has had time to bring to us, filtered through billions of years of cosmic expansion. Beyond it, current understanding strongly suggests the universe continues much as it does within it, filled with galaxies, stars, and the same vast cosmic structures we observe closer to home. We simply cannot see that far, not because there is nothing there, but because the light from those regions has not yet had the time, even accounting for the age of the universe, to complete its journey to us. As we continue through this documentary, we will explore what lies at the very outer edge of what we can observe, the oldest light of all, a faint glow that fills the entire sky and marks the boundary of what any telescope, however powerful, will ever be able to detect using ordinary light. This ancient glow and the story of how it came to exist will be our next stop on this long, slow journey outward. If you were to point the most sensitive instruments available anywhere in the sky, in any direction at all, you would eventually detect something remarkable, a faint, steady glow of microwave radiation, present everywhere, in every part of the sky, at almost exactly the same intensity, no matter which way you look. This is known as the cosmic microwave background, and current understanding holds that it represents the oldest light human instruments have ever been able to detect. A kind of afterglow left behind from a time when the universe was almost unimaginably young, hot, and dense. To understand why this glow exists, and why it forms such a natural boundary to what we can observe, we need to travel back, in our imagination, to the very early universe, a time long before galaxies, stars, or planets had formed. In this early period, the universe was filled with an extremely hot, extremely dense soup of particles, protons, electrons, and photons, all tightly bound together, constantly colliding with one another. Under these conditions, light could not travel freely. A photon attempting to move through this dense fog would almost immediately collide with a free electron, scatter off in a new direction, and be absorbed or redirected again almost at once. The early universe, in this sense, was opaque, filled with light, but light that could not travel any meaningful distance without being interrupted. As the universe continued to expand, it also continued to cool, in much the same way that any expanding gas tends to cool as it spreads out. Eventually, roughly 380,000 years after the universe began, a relatively brief span of time on cosmic scales, the temperature dropped low enough for something important to happen. Protons and electrons, which had until then been kept apart by the intense heat and constant collisions, were finally able to combine and form neutral hydrogen atoms. Once this happened, on a truly vast scale throughout the universe, something remarkable occurred. The fog lifted. With electrons now bound into atoms rather than floating freely, photons of light were suddenly able to travel in straight lines, largely unobstructed, for the first time in the universe's history. This moment is sometimes referred to as recombination, and the light that last scattered at that time was finally able to begin traveling freely through the universe, traveling largely undisturbed all the way to the present day. This is the light we now detect as the cosmic microwave background. It set off on its journey roughly 13.8 billion years ago, and in that time, it has stretched enormously as the space it has been traveling through has itself expanded, its wavelength lengthening from what was once visible or even higher energy light into the microwave region of the spectrum, which is why it appears today not as a glow of visible light, but as a faint whisper of microwave radiation. One of the most fascinating aspects of the cosmic microwave background is the way it appears to surround us in every direction, as though it were the inner surface of a great enclosing shell. It is important to be very careful with this image because it can easily be misunderstood. The cosmic microwave background is not a physical shell that exists somewhere out in space, centered specifically on the Earth or on our galaxy. It is, once again, a horizon of the same essential kind we discussed earlier, the outer limit of what our light-based instruments can detect, formed by the fact that light last scattered around the era of recombination has taken almost the entire age of the universe to reach us. Wherever you happen to be in the universe, in our galaxy, in a galaxy billions of light years away, anywhere at all, you would see this same faint glow surrounding you in every direction. marking the same essential boundary, the most distant moment in time from which light can, even in principle, ever reach you. It is, in a very real sense, the ultimate example of the idea we explored earlier, that every observer sits at the center of their own observable sphere. The cosmic microwave background is not centered on Earth in any special way. It appears to surround every observer, everywhere, because it marks the edge of what any observer's light can ever show them. It is worth pausing to appreciate just how remarkable it is that this ancient light can still be detected at all, after so many billions of years of travel. And it is equally worth understanding clearly why we cannot see any further back than this using ordinary light. Before the moment of recombination, the universe was, as we described, an opaque fog of scattering particles. No matter how sensitive our instruments become, no matter how far our technology advances, we will never be able to use visible or microwave light to peer directly into that earlier, foggy period, for the simple reason that light itself could not travel freely through it. The cosmic microwave background represents an absolute boundary, not because our equipment is insufficiently advanced, but because the physical conditions of the early universe make anything earlier fundamentally invisible to light-based observation. There is a gentle irony worth sitting with here. The oldest light we can see is, in some sense, not a picture of the earliest universe at all, but a picture of the precise moment the universe became transparent, the moment light was finally set free to travel. Everything that came before that moment remains hidden behind this glowing curtain, not lost necessarily, but inaccessible to us through the ordinary means of looking. Some researchers hope that other signals, gravitational waves for instance, which are not blocked by the same scattering process, might one day allow us to glimpse even earlier moments in cosmic history. But for now, and for the foreseeable future, the cosmic microwave background remains the oldest light, the most distant horizon, and the natural outer boundary of the observable universe as we currently understand it. As we continue this journey, it is worth carrying this image gently with you, a faint, ancient glow present in every direction, marking not a wall in space, but a wall in time, the moment, nearly 14 billion years ago, when the universe first became transparent enough for light to begin its long, patient journey toward us. Let us now imagine something that no spacecraft could ever actually achieve, but which is useful as a thought experiment for understanding just how strange and slippery the edge of the observable universe truly is. Imagine a spacecraft leaving Earth, traveling in a straight line in some particular direction for a very long time, years, centuries, perhaps far longer still. What would happen to the edge of what this spacecraft could observe as it made its long journey outward? The first and most important thing to understand is that the spacecraft would never approach a fixed boundary in the way it might approach, say, a distant island while sailing across an ocean. There is no wall out there for it to draw nearer to. Instead, something more subtle and more interesting would occur. As the spacecraft moved farther from Earth, its own observable universe would gradually shift, forming a new sphere, centered not on Earth, but on the spacecraft's own current position. As the spacecraft moved away from Earth, its observable region would gradually become different from ours. The collection of light able to reach it at each moment would be centered on its own changing position and shaped by the path it had taken through space and time. Over a sufficiently long journey, the traveler could receive light from regions that remain outside Earth's view, while losing access to some signals that could still reach observers left behind. The exact pattern would depend on the spacecraft's speed, direction, and the expansion of the universe. In other words, the traveler would acquire a different observable universe. It would not move closer to one fixed outer edge. Its view would continue to change around it as it traveled. And yet, curiously, no matter how far the spacecraft traveled, it would still find the cosmic microwave background surrounding it in every direction, just as it does for us. This is one of the more wonderful and strange consequences of the way these horizons work. The cosmic microwave background is not a fixed shell sitting at a particular location in space, waiting to be approached or receded from. It marks a boundary in time, the most ancient moment from which light can reach any given observer. And because that boundary is defined by time rather than by a fixed location, every observer, wherever they are and however far they have traveled, continues to see it surrounding them, always at roughly the same relative distance, still appearing as a distant surface of ancient light, although its observed details would depend on the traveler's motion and the cosmic era. This is a genuinely difficult idea to hold in the mind, because it runs so strongly against our everyday intuitions about travel and distance. If you drive toward a mountain, the mountain gets closer. If you sail toward an island, the island grows larger on the horizon. But if you travel toward the edge of the observable universe, the edge does not get closer in any meaningful sense. It simply reforms itself around your new position, precisely as it did around your old one. It may help, cautiously, to reach for the familiar image of a fog bank or the horizon at sea. If you are standing on the deck of a ship, surrounded by fog, you might see visibility extending perhaps a few hundred meters in every direction, with everything beyond that soft grey distance hidden from view. If you were to start walking, or if the ship began to sail, toward what appeared to be the edge of the visible fog, you would not actually reach any kind of wall or barrier. The visible edge of the fog would simply reform around your new position, always the same rough distance away, always surrounding you in every direction. This happens not because the fog is somehow chasing you, but because the edge you are seeing was never a physical object to begin with. It was simply the limit of how far you could see through the fog's particular density, from wherever you happened to be standing. This analogy captures something true and useful about the cosmic horizon, but it is important, in the spirit of honesty that we have tried to maintain throughout this journey, to be clear about where the comparison breaks down. Fog thins visibility because light scatters off countless tiny water droplets suspended in the air, a process of physical obstruction. The cosmic horizon exists for an entirely different reason. Not because anything is blocking or scattering the light along the way, but because there has simply not yet been enough time since the universe began for light from beyond a certain distance to complete its journey to us. Fog is a matter of physical obstruction. The cosmic horizon is a matter of time and light speed, layered on top of the ongoing expansion of space itself. The two situations produce a similar experience, an edge that recedes as you approach it, but for genuinely different underlying reasons. There is one further point worth dwelling on gently before we move on. As our imagined spacecraft continued its journey, and as its observable universe reshaped itself again and again around its shifting position, it would never once find itself outside the universe, looking back at it from some external vantage point. There is no edge to arrive at, no boundary to cross, no outside from which to observe the whole from beyond. Wherever the spacecraft traveled, however far, it would always find itself still within the same vast, ongoing universe, still surrounded by its own private horizon, still very much at the center of its own particular slice of the observable cosmos. This idea that every observer, wherever they are and however far they travel, carries their own horizon along with them, is perhaps the single most important thread running through this entire journey. It will return again in different forms and different contexts as we continue. For now, let it simply settle, quietly, into the back of your mind, the way a familiar tune might settle in after being heard a few times. The edge is not a place. It is a relationship between an observer, the speed of light, and the age of the universe. And that relationship follows you wherever you go. Let us return for a moment to something closer to home. The ordinary, everyday horizon you might see while standing on a beach, or a hilltop, or an open plain. This familiar, terrestrial horizon shares something important in common with the cosmic horizon we have been discussing, and understanding the similarities as well as the differences can help deepen our sense of why the edge of the observable universe behaves the way it does. If you stand on a beach and look out to sea, you will see the ocean apparently curving away from you, disappearing beneath a line where sky meets water. This line is the horizon, and it exists for a very simple, well-understood reason. The Earth is curved, and beyond a certain distance, its surface curves downward beneath your line of sight, eventually hiding more distant parts of the ocean from view. If you were to begin walking toward that horizon, you would never reach it, and you would never see it draw noticeably nearer. Instead, it would continually reform ahead of you, always the same rough distance away, always retreating exactly as fast as you approached. This happens not because the horizon is a real object fleeing from you, but because it is not an object at all. It is simply the description of a geometric relationship between your height above the ground, the curvature of the Earth, and the distance light can travel in a straight line before that curvature carries the surface out of view. Walking toward the horizon does not change this relationship in any meaningful way, which is why the horizon appears to move with you, always staying just out of reach. The cosmic horizon operates on a similar underlying principle, an edge defined not by a physical object, but by a relationship. But the specific relationship involved is considerably more intricate, and it is worth taking care to understand precisely how it differs from its terrestrial cousin. The Earth's horizon depends on geometry, the curvature of a solid surface, and the straight-line travel of light across relatively short distances. The cosmic horizon, by contrast, depends on the finite speed of light combined with the finite age of the universe, layered together with the ongoing expansion of space itself over enormous stretches of time. It is, in this sense, a horizon built not out of curved ground, but out of curved time, or more precisely, out of the interplay between time, light, and the stretching of space. There is another important difference worth dwelling on. When two people stand at different points along the same beach, their horizons, though centered on themselves individually, still largely overlap, because the distances involved are small compared to the size of the Earth, and both people are looking out across the same relatively modest curve of ocean. In the cosmic case, however, the overlaps and differences between observers' horizons can become enormously significant, especially across vast distances. An observer in a galaxy several billion light-years away from us would have an observable universe that overlaps with ours in some regions, but which also extends to include vast stretches of space we simply cannot see, and which excludes other vast stretches that we can see perfectly well from here. This means that no single observer anywhere in the universe has access to a complete view of everything that exists. Each observable universe is a kind of partial map, generous in its own way, but necessarily incomplete, shaped entirely by the observer's particular location in space and their particular moment in time. It is a humbling thought, in its quiet way. However powerful our telescopes become, however far our understanding advances, we will only ever see the portion of the universe that light has had time to bring to us, from our own particular corner of an unimaginably larger whole. It is worth returning briefly to the walking metaphor, because it captures something valuable about why no journey, however long, could ever close this gap. Just as walking toward the terrestrial horizon does nothing to reduce the curvature of the Earth, traveling toward the cosmic horizon does nothing to increase the age of the universe, or to grant light more time than it has already had to travel. The relationship that defines the horizon remains essentially unchanged by the traveler's motion, at least in any way that would allow the horizon itself to be reached and crossed. This is why, no matter how the details of the analogy differ, the essential experience remains strikingly similar, an edge that always seems to recede exactly as quickly as you approach it, not out of any deliberate evasion, but simply because it was never a fixed point to begin with. As we move forward into the next part of our journey, we will look more closely at exactly why space stretches in the way it does, what cosmic expansion actually means, how astronomers came to understand it, and why it does not require and does not imply that the universe has any particular center from which everything else is expanding outward. This idea of expansion sits quietly underneath almost everything we have discussed so far, and it deserves a slow, careful examination of its own. One of the most important discoveries in the history of astronomy is that the universe is not static. It is not a fixed, unchanging backdrop against which galaxies simply drift about, as ships might drift across a calm and unchanging sea. Instead, current understanding holds that space itself is expanding, that the distances between galaxies on the largest scales are steadily increasing over time, not because those galaxies are flying apart through some fixed background of empty space, but because the space between them is itself growing. This is a genuinely subtle distinction, and it is worth taking real care over it, because it is very easy to picture cosmic expansion incorrectly. The natural instinct, when told that galaxies are moving apart from one another, is to imagine something like an explosion. Countless fragments hurled outward from some central point, each one traveling through a fixed, pre-existing space. But this is not the picture that current cosmology supports. Rather than galaxies moving through space, away from some central location, it is space itself that is expanding, carrying the galaxies along with it, rather like distant landmarks on a slowly inflating landscape, gradually drawing farther apart from one another, even though none of them are, in any meaningful local sense, actually moving. The primary evidence for this expansion comes from a phenomenon known as redshift. When we examine the light arriving from distant galaxies, we can compare it against the known patterns of light produced by familiar elements, hydrogen, helium, and others, patterns that have been carefully measured in laboratories here on Earth. What astronomers consistently find is that these familiar patterns, when observed in light from distant galaxies, appear shifted toward longer, redder wavelengths than they should. This shift is known as redshift, and its size tends to increase, generally speaking, with the distance to the galaxy in question. More distant galaxies typically show a greater redshift than closer ones. It is worth being precise about what causes this redshift, because there are, in fact, different underlying mechanisms that can produce similar effects, and cosmologists are careful to distinguish between them. A small portion of the redshift seen in nearby galaxies can be attributed to their own individual motion through space, in much the same way that sound waves from a moving ambulance shift in pitch as it approaches and then recedes. But for the vast majority of distant galaxies, the dominant cause of their redshift is not motion through space at all, but the stretching of space itself, occurring continuously throughout the light's long journey toward us. As a photon of light travels across billions of years, moving through space that is itself gradually expanding, the light's own wavelength stretches along with the space it is passing through, shifting it steadily toward the red end of the spectrum. This is often referred to as cosmological redshift, to distinguish it clearly from the more familiar type of redshift caused by an object's individual motion. One of the more delicate and important points to appreciate is that this expansion does not require and does not imply any particular center to the universe. This can feel deeply counterintuitive at first. If everything is moving apart from everything else, surely there must be some central point that everything is moving apart from. But this intuition, reasonable as it feels, does not hold up under closer examination, and two gentle analogies, commonly used by astronomers, can help illustrate why. The first is the image of a balloon, with small dots marked on its surface, gradually being inflated. As the balloon expands, every dot moves farther away from every other dot, and crucially, there is no single dot on the surface of the balloon that could reasonably be described as the center of this expansion. Every dot, from its own point of view, sees every other dot moving away from it, and every dot would be equally justified in believing itself to be the center of the expansion. The true center, if the balloon has one at all, lies at the center of the sphere itself, a three-dimensional point that does not exist anywhere on the balloon's own two-dimensional surface. This analogy is useful because it captures the idea of expansion without a center within the expanding space itself. But it is important to note where it breaks down. Our universe, as far as current understanding suggests, is not a two-dimensional surface wrapped around some larger three-dimensional shape in the way a balloon's surface is. The analogy borrows the balloon's surface to represent the whole of space, without implying that our actual three-dimensional universe is curved around some further, unseen dimension in quite the same literal way. The second common analogy involves a loaf of raisin bread rising in an oven. As the dough expands, every raisin embedded within it moves farther away from every other raisin, and once again, no single raisin occupies a privileged central position. Each one, from its own perspective, would observe every other raisin receding from it in every direction. This analogy has the advantage of being fully three-dimensional, which makes it, in some ways, a closer match to our actual universe than the balloon's curved surface. But it, too, has its limits. A loaf of bread has an outer crust, an edge to the dough itself, whereas current evidence suggests that our universe, so far as we have been able to measure, shows no sign of any such edge or boundary within the space we can observe. Perhaps the most important thing to take from both of these analogies is not their specific details, but the shared lesson they both point toward. Expansion does not require a center. It is entirely possible, and indeed appears to be the case, for every point within an expanding system to see every other point moving away from it, without there being any single privileged location from which the expansion is originating. Wording that suggests the universe is expanding into some surrounding empty space, the way a balloon expands into the room around it, is misleading, and it is worth being cautious of such phrasing wherever it appears. As far as current observations and models suggest, there is no external space for the universe to expand into. The expansion describes the increasing distance between points within space itself, not the movement of space into some larger container beyond it. This idea of an expansion without a center, difficult as it may be to fully picture, lies at the very heart of why the cosmic horizon behaves the way it does, why it moves with every observer, why it never resolves into a fixed, approachable boundary, and why every point in the universe can, with equal justification, consider itself to be at the center of its own observable region. As we continue forward, we will look more closely at one of the most striking consequences of this ongoing expansion: the existence of galaxies whose light we can see perfectly well tonight, but which we will nevertheless never be able to reach, and which may, in a very real sense, already be lost to us forever. There is something quietly poignant about a particular category of galaxies scattered throughout the night sky. Galaxies whose ancient light reaches us perfectly well, glowing faintly in telescope images taken here on Earth, and yet which, current understanding strongly suggests, we could never reach, never visit, and in many cases, never even send a message to, no matter how much time we were given or how advanced our technology became. To understand why this is so, we need to return once more to the distinction between light travel distance and present-day distance, which we touched upon earlier, and add one further layer of understanding on top of it: the difference between merely seeing a galaxy and being able to reach it or communicate with it in any meaningful sense. When we observe a very distant galaxy, we are, as we have discussed, seeing light that set off on its journey a very long time ago, potentially billions of years in the past. Because the universe has continued expanding throughout that entire journey, the galaxy that originally sent this light is now, at this very moment, considerably farther away than it was when the light departed. In many cases, the ongoing expansion of space has carried that galaxy so far away that the distance between us and its present-day location is now increasing faster than light could ever cross it. This can sound, at first hearing, as though it must violate some fundamental law of physics, surely nothing can move faster than the speed of light. And this is true as far as it goes. Nothing can move locally, through space, faster than light. But the expansion of space itself is not a form of local motion in this sense. It is the space between 2 points that is stretching, and over sufficiently large distances, the combined effect of countless small stretches, added together across billions of light years, can result in the distance between 2 points increasing at a rate that exceeds the speed of light, without either point ever having to move through its own local space any faster than light is permitted to travel. This is a subtle distinction, but it is a genuine and well-understood feature of current cosmological models, not a loophole or a contradiction. The practical consequence of this is significant and worth stating plainly. A great many galaxies visible in our telescopes are currently receding from us at an effective rate greater than the speed of light because of the expansion of the space between us. That fact alone does not necessarily make a galaxy unreachable. The decisive question is whether it lies beyond our cosmic event horizon, the boundary beyond which a signal sent today can never arrive, even over unlimited time. For galaxies beyond that horizon, a radio message or beam of light sent today would continue traveling locally at the speed of light. Yet the changing geometry of the expanding universe would prevent it from ever reaching its destination. It would set off, traveling at the fastest speed the universe allows, and yet the space between us and its destination would continue to stretch faster than the signal could close the gap, meaning the message would never reach its target, no matter how much time passed. This boundary, the distance beyond which a signal sent today could never reach its destination, is known as the cosmic event horizon, and it is a genuinely distinct concept from the observable universe we discussed earlier. The observable universe describes everything whose past light has already had time to reach us. The cosmic event horizon, by contrast, describes the boundary beyond which our future light, sent out from today onward, could never reach, no matter how long we waited. It is entirely possible, and indeed appears to be the case, for a galaxy to lie within our observable universe, meaning we can see it perfectly well, using light it sent long ago, while simultaneously lying beyond our cosmic event horizon, meaning that we could never send it a message or reach it, even in principle, using any signal or spacecraft, however swift. This does not mean these distant galaxies are doing anything unusual or dramatic. They are not fleeing from us at extraordinary local speeds, nor are their inhabitants, if any exist, experiencing anything out of the ordinary within their own corner of space. From their own local perspective, everything around them would appear entirely normal. Their own stars would shine steadily. Their own local region of space would show no sign of unusual stress or distortion. It is only the relationship between their location and ours, stretched by the accumulated effect of cosmic expansion over enormous distances, that has grown to the point where no signal could ever bridge the gap. It is worth offering a note of reassurance here, closer to home. Not everything in the universe is subject to this ongoing separation. Galaxies that are gravitationally bound to one another, held together by the mutual pull of their own gravity, strong enough to overcome the influence of cosmic expansion, do not drift apart in this way. Our own galaxy, the Milky Way, together with the Andromeda Galaxy and a modest collection of smaller companion galaxies, forms what is known as the local group, a cluster of galaxies bound together tightly enough by gravity that the expansion of space at these comparatively small distances has essentially no power to pull them apart. In fact, rather than drifting away from us, the Andromeda Galaxy is currently moving closer, drawn inward by the gravity of the local group. Current models suggest that the Milky Way and Andromeda may undergo a close encounter and eventually merge several billion years from now, although meaningful uncertainty remains about the exact path, timing, and final outcome. Whatever form their future interaction takes, the local group is expected to remain gravitationally bound, even as the wider universe continues to expand. So, we are left with a strange and rather beautiful picture. The night sky is filled with light from galaxies scattered across a vast range of distances, some nearby, gravitationally tied to our own small cluster, destined to remain our neighbors for the whole of the foreseeable future, and others impossibly distant, their ancient light still arriving faithfully after journeys lasting billions of years, even though the galaxies that sent it have long since drifted beyond any hope of ever being reached. We can see them. We can study their light, learn about their structure, their composition, the era of the universe they represent. But reaching them, in the most literal sense, is now, and likely will forever remain, entirely beyond our grasp. Let us imagine, once again, a journey that no real spacecraft could ever actually undertake, but which is useful for exploring the deeper implications of everything we have discussed so far. Suppose it were somehow possible to build a spacecraft capable of traveling at a significant fraction of the speed of light, not quite reaching it, since current understanding of physics holds that nothing with mass can ever quite reach the speed of light itself, but close enough that its effects would become extraordinarily pronounced. The first obstacle such a spacecraft would face is a very practical one: the sheer amount of energy required to accelerate any object with mass to speeds approaching that of light grows dramatically and disproportionately the closer that object gets to light speed itself. Doubling a spacecraft's speed does not simply double the energy required to achieve it. As an object's velocity climbs closer and closer to the speed of light, the energy needed for each further increase in speed grows without any apparent limit, approaching what would, in principle, require an infinite amount of energy to actually reach light speed itself. This is one of the principal reasons why current physics regards travel at the speed of light, for anything possessing mass, as fundamentally unreachable, rather than merely difficult from an engineering standpoint. Setting aside, for the moment, the question of how such tremendous energy might ever be gathered, let us imagine that our spacecraft has somehow managed to reach a very high fraction of light speed, perhaps 99%, or higher still. At these extraordinary velocities, a range of strange and genuinely well-established effects would begin to emerge, collectively described by the theory of relativity, first developed in the early 20th century and confirmed many times over by subsequent observation and experiment. Foremost among these effects is time dilation. From Earth's frame of reference, clocks aboard the fast-moving spacecraft would run more slowly. The travelers, however, would experience their own clocks and daily lives normally, because observations are also affected by changing distance, signal delay, and relativistic Doppler effects. Neither side would simply watch the other's entire world running at one steady altered speed. The clearest comparison would come if the travelers later reunited with observers on Earth. Less time would have elapsed for those who made the high-speed journey. This is not merely an illusion caused by delayed light signals. It reflects a genuine difference in the amount of time experienced along the two paths. The practical consequence of this is striking. A traveler aboard a spacecraft moving at a sufficiently high fraction of light speed could, in principle, experience a journey of only a few years of their own personal time, while many decades, centuries, or even longer might pass back on Earth during that same interval. This does not allow the traveler to outrun the cosmic horizon in any meaningful sense. However, because although their own personal experience of time would be compressed, the universe outside their windows would still be following its own timeline, expanding at its usual rate, with the cosmic horizon continuing to recede exactly as it does for any other observer. The traveler's compressed sense of time would allow them to cross vast distances within their own limited lifespan, but it would not allow them to catch up with, or overtake, the fundamental relationship between light, time, and cosmic expansion that defines the observable and reachable universe for any observer, however swiftly they happen to be moving. There would also be striking visual effects for our imagined near-light-speed traveler. Light from objects ahead of the spacecraft would appear shifted toward the blue end of the spectrum, a phenomenon known as blue shift, caused by the spacecraft's own motion compressing the wavelength of incoming light. Light from objects behind the spacecraft, meanwhile, would appear shifted toward the red end of the spectrum, stretched by the increasing distance opening up behind the ship. At sufficiently extreme speeds, these shifts could become dramatic enough to move visible light entirely out of the range the human eye can perceive, with light from directly ahead shifting into ultraviolet or beyond, and light from directly behind fading into infrared or beyond, potentially leaving much of what was once a richly star-filled view appearing strangely dark or altered to unaided human eyes. There would be very real hazards to consider as well, setting aside for a moment the purely theoretical physics. At speeds approaching a significant fraction of light speed, even the extremely sparse interstellar medium, the thin scattering of gas and dust particles that fills the seemingly empty space between stars, would present a serious danger. Individual particles, ordinarily harmless at rest, would strike the front of a fast-moving spacecraft with tremendous energy, potentially causing significant damage over the course of a long journey, and posing serious risks from radiation exposure to any living crew aboard. These are genuine engineering and safety challenges that any realistic future attempt at high-speed interstellar travel would need to overcome, quite separate from the more abstract questions of energy requirements and relativistic time effects. Bringing all of this together, we arrive at a rather beautiful, if slightly melancholy, conclusion. Even a spacecraft traveling at the very highest speeds, current physics considers plausible, experiencing dramatic compression of its own onboard time, capable of crossing enormous distances within a single human lifetime, would still never be able to catch the cosmic horizon, still never be able to arrive at some fixed edge of the universe, and would still, wherever it finally came to rest, find itself surrounded by its own private observable sphere, with its own version of the cosmic microwave background glowing steadily in every direction, precisely as it does for us, here on Earth, moving through space at our own comparatively gentle pace. Having spent considerable time exploring the observable universe and the various horizons that limit what we can see and reach, it is worth turning our attention to a related but genuinely distinct question. Does the universe as a whole, not merely the portion we can observe, but the entire universe, in its full extent, have an edge at all? This is a question current science has not fully answered, and it is important, in the spirit of honesty we have tried to maintain throughout, to be clear about precisely where established observation ends and where careful, reasoned speculation begins. There are, broadly speaking, a small number of possibilities that cosmologists consider when thinking about the overall shape and extent of the universe. One possibility is that the universe is genuinely infinite, that it extends forever in every direction, without any boundary or edge of any kind, containing an infinite amount of space, and very likely, though this too remains uncertain, an infinite number of galaxies, stars, and everything else that fills the cosmos. An infinite universe of this kind would have no edge to reach, not because the edge is impossibly distant, but because there would be no edge in existence at all, however far one traveled. A second possibility is that the universe is finite in extent, but nonetheless without any boundary or edge, a concept that sounds, at first hearing, almost like a contradiction, but which becomes considerably easier to grasp with the aid of a carefully chosen analogy. Consider the surface of the Earth. If you were to set off traveling in a single direction and continue traveling in as straight a line as the Earth's surface allowed, you would never encounter an edge, a wall, or a boundary of any kind. And yet the surface of the Earth is not infinite. It has a finite, measurable area. The resolution to this apparent puzzle lies in the fact that the Earth's surface is curved, wrapping back around on itself in a way that allows it to be finite in total area while having no edge anywhere upon it. A sufficiently patient traveler, walking in a perfectly straight line for long enough, would eventually find themselves back where they started, having circled the entire globe without ever once encountering a boundary. Some cosmological models propose that the universe as a whole might be shaped in a broadly similar way, though extended into 3 spatial dimensions rather than the 2 dimensions of the Earth's curved surface. A genuinely difficult thing to picture directly, since we are not able to step outside our own 3-dimensional space and view its curvature from some further dimension, the way we can step back and view the curved surface of the Earth from space. Mathematically, however, such a shape is entirely coherent, and cosmologists are able to describe and study its properties using the tools of geometry, even without being able to visualize it directly in the way we can visualize a curved 2-dimensional surface. There are, in fact, a range of possible topologies, overall shapes, that a finite, unbounded universe of this kind might take, some considerably more exotic than a simple curved sphere, including shapes where a traveler moving in a straight line might eventually encounter a kind of repeating pattern. Seeing the same distant galaxies appear in multiple different directions in the sky, having wrapped around some more complex, folded geometry. Current observational evidence has not detected any convincing sign of such repeating patterns, which places meaningful, though not absolutely definitive, limits on how small and how exotically shaped such a folded universe could plausibly be. So which of these possibilities does the evidence actually favor? Here we must be especially careful and precise. Detailed measurements of the cosmic microwave background, along with a range of other observational techniques, have allowed cosmologists to measure the overall geometry of the observable universe with considerable precision. And these measurements consistently suggest that, on the larger scales we are able to observe, space appears to be very close to what mathematicians call flat, meaning that within the region we can measure, the familiar rules of ordinary geometry, the kind learned in school, involving parallel lines and the angles of triangles, appear to hold true with a very high degree of accuracy. This finding of flatness is often, understandably, taken as suggestive evidence in favor of an infinite universe, since a perfectly flat geometry, extended without limit, would indeed produce an infinite space. But it is essential to state clearly, and without exaggeration, that spatial flatness within the observable universe does not, on its own, prove that the universe as a whole is infinite. A universe that is finite but extremely large, far larger than the portion we are able to observe, could easily appear flat within the comparatively small region accessible to our measurements, in much the same way that the surface of the Earth, despite being a curved sphere, appears essentially flat to someone standing in a broad, open field, simply because the region they can directly examine is so small compared to the Earth's overall size. This is, in truth, one of the genuine open questions at the frontier of modern cosmology. Current observations are consistent with an infinite universe. They are also consistent with a very large, but ultimately finite, universe, provided that its true size significantly exceeds the portion we are able to observe. Distinguishing definitively between these possibilities would require either detecting subtle repeating patterns in the distribution of distant galaxies or the cosmic microwave background, patterns that no observation has yet convincingly revealed, or some other form of evidence not currently available to us. Within our present understanding, the honest and accurate answer to the question of whether the universe has a true edge and whether it is finite or infinite in its overall extent remains genuinely unknown. What can be said with much greater confidence is this: whether the universe turns out to be infinite or merely unimaginably, almost incomprehensibly large, there is no reason, based on any current evidence, to think that it possesses anything resembling the kind of edge most people initially imagine when they first ask the question. No wall, no boundary, no abrupt stopping point, standing somewhere out in space, waiting patiently to be reached by a sufficiently determined traveler. Given everything we have discussed so far, a natural question arises: what does current understanding suggest actually lies beyond the observable universe, beyond the farthest boundary our telescopes will ever be able to detect? It is important, before proceeding, to draw a clear and careful line between what can reasonably be inferred from established physics and what remains, honestly and explicitly, in the realm of speculation. The most straightforward and best supported expectation among cosmologists is that the region of space beyond our observable universe very likely continues to look much like the region we can see. This is not merely a hopeful guess. It follows naturally from a principle that has been consistently supported by everything we have observed within the portion of the universe accessible to us. On the larger scales we are able to examine, the universe appears remarkably uniform, filled with roughly the same density of galaxies, arranged into roughly similar large-scale structures in every direction we look and at every comparable distance we are able to measure. There is no evidence of our own corner of the universe being unusual, special, or different in character from any other region we can observe. Extending this same principle outward, beyond the edge of what we can currently detect, the most reasonable expectation is that the universe simply continues. More galaxies, more stars, more of the same essential large-scale structure, stretching on for some considerable distance beyond our current horizon, and quite possibly very much farther still. It is worth emphasizing this point clearly, because it is easy, without meaning to imagine the unseen regions beyond our horizon as somehow strange, exotic, or fundamentally different from the universe we know. Current understanding offers no support for this idea. The unseen universe, so far as reasonable inference can suggest, is not automatically exotic. It is, in all likelihood, simply more of the familiar cosmos, continuing on beyond the point where our light-gathering instruments finally run out of light to gather. One of the most important theoretical frameworks supporting this expectation is a concept known as cosmic inflation, a proposed period of extraordinarily rapid expansion thought to have occurred in the first tiny fraction of a second after the universe began, long before the era that produced the cosmic microwave background we discussed earlier. Inflation was originally proposed to help explain several otherwise puzzling features of the universe we observe today, including its remarkable large-scale uniformity and its close-to-flat geometry. And while it remains, honestly, a leading model rather than an absolutely settled fact, it has gathered substantial indirect observational support over the decades since it was first proposed. One of the striking implications of many inflationary models is that the brief period of extraordinarily rapid expansion, if it occurred as proposed, would very likely have stretched the universe to a size vastly, almost incomprehensibly, larger than the portion we are able to observe today. Under many versions of this model, the full universe, the entire region produced by inflation, of which our observable universe forms only the tiniest visible fraction, would extend far, far beyond anything we could ever hope to detect. Even in principle, given the fundamental limits imposed by the finite speed of light and the finite age of the universe since inflation ended. This is a genuinely humbling idea to sit with. If current inflationary models are broadly correct, then the observable universe, vast as it already seems, with its billions of galaxies and its diameter of roughly 92 billion light-years, may represent only an almost unimaginably small fragment of a far larger whole. A whole so extensive that no observer, anywhere within it, could ever hope to see more than the tiniest local patch, forever isolated from the vast majority of everything that exists by nothing more dramatic than the ordinary limits of light and time. It is essential, at this point, to be extremely careful about the difference between inference and direct observation. We cannot directly observe anything beyond our own horizon. Every statement about the likely continuation of galaxies, structure, and space beyond that boundary is, honestly speaking, an inference, a reasonable extrapolation grounded in well-tested physical principles and in the uniformity we observe within our own accessible region, but an inference nonetheless, not a direct measurement. Cosmologists take considerable care to distinguish between the strong, direct evidence supporting the broad framework of an expanding, roughly uniform universe within the observable region, and the necessarily more tentative extrapolations required to say anything at all about what lies beyond it. This brings us, finally, and with appropriate caution, to a topic that occasionally arises in discussions of what may lie beyond our cosmic horizon: the idea of a multiverse. Some theoretical frameworks, including certain versions of inflationary theory, suggest the intriguing, if highly speculative, possibility that our own universe might be just one among many separate regions, sometimes described as bubble universes, each potentially governed by its own particular physical conditions, forever disconnected from one another by distances and processes that make any form of contact or observation between them effectively impossible. It is important to state, clearly and without embellishment, that this idea remains firmly speculative. It has not been confirmed by any direct observation, and given the nature of what it proposes, regions fundamentally beyond the reach of any possible observation from within our own universe, it may, by its very nature, never be possible to confirm or refute it through direct evidence in the way most scientific ideas eventually are. It remains, for now, an interesting and mathematically motivated extension of certain physical theories rather than an established feature of our cosmological understanding, and it is best held loosely, with appropriate curiosity, rather than mistaken for settled scientific fact. What we can say, with far greater confidence, is this. Current evidence and current theory together suggest that our observable universe, remarkable as it is, likely represents only a small, local window onto a far larger cosmos. One that very probably continues, in broadly familiar form, well beyond anything we could ever hope to see, stretching outward into a vastness that may be finite, but staggeringly large, or may quite possibly have no ultimate limit at all. Let us now allow our thoughts to drift forward in time, far beyond the present moment, into a distant future that current models of cosmic expansion allow us to describe, at least in broad and careful outline. If the expansion of the universe continues in the manner current observations suggest it will, then the night sky, as seen from Earth, or more precisely, from whatever remains of our galaxy in the far future, will undergo a slow, gradual, almost imperceptible transformation across an immense span of time. The essential process at the heart of this transformation is one we have already encountered. Galaxies that are not gravitationally bound to our own local group will, over the course of many billions of years, continue to recede from us, carried outward by the ongoing expansion of space at an ever-increasing rate. Many of these galaxies, as we discussed earlier, already lie beyond our cosmic event horizon, meaning any light or signal we might send toward them today could never arrive. But their existing light, sent long before that boundary was crossed, continues to reach us even now, and will continue to do so for an extremely long time to come, even as its character gradually, steadily changes. As the space between us and these distant galaxies continues to stretch, the light we receive from them will become increasingly redshifted, its wavelength growing steadily longer, shifting further and further from the visible spectrum, eventually moving into infrared, then into radio wavelengths far too long for any current optical telescope to detect. This is a gradual fading, rather than an abrupt vanishing. Distant galaxies will not blink out of existence from our perspective in any sudden or dramatic fashion. Instead, they will grow dimmer and dimmer, their light stretching to ever longer wavelengths, becoming ever more difficult to detect, slowly withdrawing from view over the course of an almost unimaginably long stretch of cosmic time, extending many billions and eventually trillions of years into the future. Given a sufficiently long span of time, far longer than the current age of the universe, extending many multiples of 13.8 billion years into the future, current models suggest that eventually, the only galaxies remaining visible from our vantage point will be those bound tightly enough by gravity to resist the pull of cosmic expansion, the future gravitationally bound descendant of the local group, which we discussed earlier. Every other galaxy, every other cluster, every other great structure currently visible in our deepest telescope images will have receded so far and become so redshifted as to become entirely undetectable for all practical purposes, effectively gone from the observable sky. This has a rather striking implication for any hypothetical astronomers who might exist in that unimaginably distant future, studying the sky from within the future gravitationally bound local group, where we today can observe billions of galaxies, study their light, measure their redshift, and use this evidence to reconstruct a detailed and compelling picture of cosmic expansion and the universe's history, those future astronomers would find themselves working with dramatically less to go on. Surrounded by an apparently empty or nearly empty sky beyond their own isolated island of stars, they might struggle to detect any direct evidence of cosmic expansion at all, since the very galaxies that would reveal it would have long since faded beyond the reach of any instrument they could plausibly construct. Even the cosmic microwave background, that faint and ancient glow, currently detectable in every direction, filling the whole sky with the afterglow of the universe's early, hot, dense phase, will not remain readily detectable forever. As the universe continues to expand, the wavelength of this background radiation will continue to stretch, just as the light from distant galaxies does, growing longer and longer, its energy spreading ever more thinly across an ever-expanding volume of space. Over sufficiently long timescales, this ancient glow, currently one of our most powerful tools for understanding the early universe, will become so stretched, so faint, and so diffuse that it will likely become effectively undetectable, even to instruments considerably more sensitive than anything we currently possess. There is something quietly poignant in this picture, worth sitting with for a moment before we move on. We happen to exist during a period in cosmic history when the evidence for the universe's origin and expansion remains richly, generously available to anyone who develops the tools and the curiosity to look for it. Billions of galaxies remain visible. The cosmic microwave background remains detectable, its faint signal still bright enough to be carefully measured and studied. Future civilizations arising in the unimaginably distant future may not be nearly so fortunate. They may inherit a sky that appears, to all appearances, calm, quiet, and largely empty beyond their own small cluster of galaxies. A sky that offers little obvious hint of the vast, dynamic, expanding universe that produced it, unless they happen to inherit and trust the careful records and observations left behind by earlier generations, looking back across time at a universe that once, long ago, was very much richer in visible galaxies than the one they themselves would be able to see. This distant future remains, it is worth remembering, an extrapolation, however well grounded in current physical understanding. It assumes that the pattern of expansion we currently observe continues in a broadly similar fashion for an extraordinarily long span of time, an assumption that current evidence supports reasonably well, but which, like everything in cosmology concerning such distant timescales, carries with it a degree of appropriate humility and uncertainty. Let us bring our attention back, for a while, to something closer and more immediate than the slow fading of the wider universe. The future of our own small corner of the cosmos, the local group, and the long gravitational relationship between the Milky Way, Andromeda, and their smaller neighboring galaxies. Unlike most distant galaxies, Andromeda is not receding from us. It is moving generally toward the Milky Way under the shared gravity of the local group. For many years, the most familiar models predicted a major collision and merger several billion years from now. More recent calculations have emphasized that the exact outcome remains uncertain. The galaxies may merge, they may experience a less direct encounter first, or their interaction may unfold over a longer period than earlier estimates suggested. Should a merger eventually occur, it would not resemble two solid objects crashing together. Galaxies are overwhelmingly empty space. Direct collisions between individual stars would be extremely rare. Instead, gravity would gradually distort the galaxies, alter stellar orbits, and reshape their gas and dust over hundreds of millions of years. Whatever the precise outcome, the local group is expected to remain gravitationally bound. Its galaxies may interact, merge, or reorganize, but cosmic expansion will not pull this local collection apart in the same way it separates distant, unbound galaxies. This brings us to a distinction worth stating clearly, because it draws together several of the ideas we have explored throughout this journey. There is a meaningful difference between the reachable universe and the observable universe, and the story of the local group's merger illustrates this difference beautifully. The observable universe, as we have discussed at length, includes an enormous number of galaxies, the vast majority of which lie beyond our cosmic event horizon, meaning we can see their ancient light, but could never send a signal to them or travel to reach them, however much time we were given. The region that is theoretically reachable is much smaller than the observable universe, but it is not strictly limited to the local group. Some galaxies beyond our local gravitational neighborhood remain within the region that signals sent today could, in principle, eventually reach. Over the deepest future, however, the local group, or whatever gravitationally bound system develops from it, would remain the enduring connected island after more distant, unbound galaxies had passed beyond practical contact and visibility. In the very long run, then, as the wider universe continues its slow fade into darkness and redshift, described in the previous section, whatever gravitationally bound system eventually develops from the Milky Way, Andromeda and their smaller companions will become something rather like an isolated island, surrounded by an increasingly dark, increasingly empty-seeming ocean of space. This is not because the wider universe will have ceased to exist. As we have discussed, current understanding strongly suggests it will continue on, filled with galaxies and structure, far beyond our own small neighborhood. It is simply that the accelerating expansion of space will have carried everything else so far away, and stretched its light so thoroughly that from within this future gravitationally bound system, that wider universe will become effectively invisible and entirely unreachable. Any future inhabitants of this distant local group descendant, looking up at their night sky many billions of years from now, would find themselves gazing at a sky filled with the stars of their own galaxy. Still numerous, still varied, still capable of hosting planets, and quite possibly still capable of hosting life, but largely devoid of the countless external galaxies that fill our own night sky with such richness today. It would be, in a certain sense, a smaller universe than the one we currently enjoy, not because the universe itself had shrunk, but because the portion of it remaining visible, and more importantly, the portion remaining reachable, would have contracted down to this single, isolated, gravitationally bound island of stars. There is a certain grace in this picture, even amid its melancholy undertones. The local group, our own small gravitational neighborhood, held together not by the vast sweeping expansion that governs the wider universe, but by the intimate, local pull of gravity between relatively nearby galaxies, will endure as a coherent, connected structure long after the rest of the observable universe has drifted beyond any hope of contact. It is, in its own quiet way, a reminder that connection, whether between galaxies or between people, tends to depend far more on what binds things closely together than on the vast, indifferent expanses that lie beyond. Let us come back now gently from these distant reaches of space and these unimaginable stretches of future time to the quiet, familiar present, to tonight, to this room, to wherever you happen to be lying as these words reach you. We have traveled a long way together across this journey, through ideas that stretch the imagination in every direction. The strange, personal nature of the observable universe, always centered on whoever happens to be looking. The way every glance upward is really a glance backward into the past. The vast, gentle stretching of space itself, carrying galaxies apart from one another without any center, any explosion, any single point of origin. The ancient, faint glow of the cosmic microwave background marking the oldest light any of us will ever see, and the slow, patient realization that no journey, however long, however fast, could ever bring a traveler to some final, fixed edge of everything that exists. It is worth gathering these threads together now, gently, one final time. The edge was never a destination. It was never a place waiting somewhere out among the stars for a sufficiently determined traveler to finally arrive at, the way a mountaineer might finally reach a distant summit after a long and difficult climb. It is instead a horizon, a boundary created not by space itself, but by the interplay of light, time, and the ongoing expansion of the universe, a boundary that reforms itself around every single observer, wherever they happen to be, and however far they have traveled. Every observer, everywhere in the universe, sits at the center of their own visible sphere. This was true for us here on Earth at the very beginning of this journey, and it remains true now, at its end. It was true for our imagined spacecraft, traveling outward for centuries, watching its own horizon reshape itself around its shifting position. It would be true for any observer, anywhere in the cosmos, on any planet, orbiting any star, in any galaxy, however near or however far. This is not a limitation unique to humanity, or to Earth, or to our own particular moment in cosmic history. It is simply a fundamental feature of what it means to observe a universe governed by a finite speed of light. The night sky above you, whenever you next have occasion to look up at it, is filled with light of many different ages, arriving from many different distances, each point of light carrying its own small fragment of history across the vast gulf of space and time. Some of that light left its source mere minutes ago. Other light has been traveling for millions, or even billions of years, departing from galaxies that may, by now, have drifted far beyond any hope of ever being reached, carried away by the quiet, patient stretching of space itself. And yet all of it arrives together, in the same dark sky, at the same moment, forming the rich, layered tapestry of ancient light that has always accompanied human beings whenever they have paused to look upward. It is worth remembering, too, that we find ourselves living during a particularly rich period in cosmic history, at least in terms of what remains available for us to see. Billions of galaxies still lie within our observable universe, their light still reaching us, still available for study, still capable of teaching us about the origins and the unfolding history of everything around us. In the almost unimaginably distant future, as we explored a little earlier, this generous abundance will slowly fade, as galaxy after galaxy drifts beyond the reach of detection, leaving future observers with a far quieter, far emptier sky to contemplate. We are fortunate, in this quiet, easily overlooked way, to exist at a moment when so much of the universe's story remains legible, written across the sky in ancient light, waiting patiently to be read by anyone who cares to look. None of this, the impossibility of ever reaching the true edge, the slow drifting away of distant galaxies, the eventual isolation of our own small corner of the cosmos in the far future, should be understood as any kind of loss, or any diminishment of meaning. The universe does not need to be reachable in its entirety to be worth wondering about. A horizon that moves with you is not a barrier keeping you from something. It is simply the shape that seeing takes, when light must travel across vast distances to reach an observer bound by the ordinary, gentle limits of time. There is a quiet comfort in this if you allow yourself to feel it. Wherever you are, wherever you go, the universe will always arrange itself gently around you, offering you a genuine, honest window onto an almost unimaginable vastness, even while keeping certain of its farthest reaches permanently, peacefully out of reach. The edge of the universe was never waiting at the end of a road. It has traveled with us from the beginning, surrounding every observer with a different boundary of visible time. It surrounded the very first humans who ever looked up at a clear night sky, and it surrounds you now, in this quiet moment, just as gently, just as faithfully. Let the vastness of it settle over you softly, the way darkness settles over a familiar room. There is nothing out there to chase, nothing left unreached that needs to be reached tonight. Nothing about this endless, gentle horizon that should keep you from resting. The stars will still be there tomorrow, exactly as far away, exactly as patient, exactly as quietly beautiful as they are tonight. Rest now, here on this small, warm world, beneath a sky filled with ancient light. Good night.